All right. Thank you, everyone, for coming to today's colloquium. We have a fantastic speaker joining us today, Antoine. Antoine did his PhD with Alan Aspect on metastable helium and thinking about forming a BEC of that. He did his postdoc in Bill Phillips' group in Gaithersburg, Maryland. And he has since then been an absolute pioneer in the field of trapping single atoms in tweezers and getting them to interact via Rydberg interactions. This has, if you don't know, this is a wildly popular field at the moment. Lots and lots of activity in the field. And it's so active that there are multiple companies that have been formed. In fact, he's helped to form a company in Paris around exactly this concept. He's going to tell us about some beautiful physics today. I'll just turn it over to him and let him tell us the story.
Thank you very much, James. So it's, as I said yesterday during a different seminar, you can hear me well, or should I? Okay, no, you cannot. So I'm going to put the thing even closer. Oh, and should speak louder. Is it better now? Yes. Okay. So as I said yesterday in the other talks, I'm very delighted to be at GILA. It's really for all of us outside the US, really the mecca where in AMO physics, but also in all kinds of physics. So I'm very, very happy to be here to see many friends and colleagues I've been meeting and knowing for now several decades. So indeed, what I'm going to talk to you about today are experiments that we've done, and of course I will try to be a bit more general than what I had been yesterday, that we've done at the Institut d'Optique over the last 15 years, so that will introduce the field, about exploring many-body physics with arrays of individual atoms. So strictly speaking, we are not in Paris, and there is this Eiffel Tower made of small atoms. We are at the Institut d'Optique, which is on the campus of Université Paris-Saclay, which is 20 kilometers south of Paris. And so this is the largest cluster of actually research labs in France. So this is a picture of our group at the Institut d'Optique at the end of last summer. So the group has shrunk a little bit. It varies depending on the number of interns. But essentially, we are like 3 permanent staff members in our group. And this is something very specific to the French system. There are many permanent staff members. So apart from myself, there is a younger staff member, Thierry, and an even younger one, Igor. And they supervise together with me like a bunch of postdoc and a PhD student. And essentially, the thing which is very important in those days for us are the collaboration that we have with people from in theory. Because I mean, we do a lot of many-body physics, I'm going to say. Most of us have been trained in AMO physics, so our views of condensed matter physics and many-body problems are very naive. So we really need a guidance, and everything we do is now done on whatever project in collaboration with theory people. And so for what I'm going to discuss today, this was essentially the work of Daniel, Guillaume, Cheng, Bastien, Gabriel, and Lucas. And we had collaboration with people at Harvard, so Norman Yao and his colleague Mike Zelletel, who was in Berkeley, and Andreas Löschli in Lausanne. So I'm going to discuss what we've done with them. In our group, with this team of people, we actually have 3 projects that all look at different aspects of quantum simulation using synthetic systems. So the first one is the one I'm going to talk about, so I'm not going to spend too much time now. So tunable arrays of atoms that we make interact by promoting them to Rydberg state. Then we have another one where we take an ensemble of atoms, we shine light, the light polarizes the atoms, so now we've got dipoles, and if those dipoles are close enough, they will interact, and we look at how this interaction modifies the way the system scatters light. And Igor has started in our group like 2 years ago, with nearly 3 now, study of this kind of system here, light scattering, but now using the tools that we have developed on arrays of Rydberg atoms, and he does that with dysprosium atoms, which is kind of a new species in the field of manipulating of individual atoms. Okay, so let me start with kind of the general view on how and why we're doing that. So the general context of what we do is many-body physics. So many-body physics, saying this way, it's essentially all physics. But the goal here is trying to understand what happens if you take an ensemble of very strongly interacting quantum particles. I mean, you need all the things like strongly interacting and quantum particles. So this is something which, of course, at a microscopic level is relevant to describe many-body physics like superfluidity, superconductivity, some aspect of magnetism, and you can also go outside the realm of traditional condensed matter physics by going to neutron star or even high-energy physics. Of course, the kind of question we're asking are, the phase diagram. Sometimes we don't even know for a given system what is the ground state of the system when you are given an Hamiltonian with a peculiar kind of couplings. Very often it's extremely difficult to understand the excitations of the system, what happens if you shake them, or the dynamics out of equilibrium. And so there is also this whole idea that is now becoming more and more popular, which is, can we use the concept of quantum information theory, like entanglement, for example, to classify the phases of matter? So this is not something that you still find in textbook in condensed matter physics, but now you've got more and more paper which try to see how we can characterize whether it's useful to introduce the concept of entanglement in the context of condensed matter physics. So of course we know what to solve. I mean, this is not at all the problem, and we have to solve the Schrödinger equation essentially, and we even know how to write the Hamiltonian. So this is a non-relativistic version, but essentially this Hamiltonian has all the solid-state physics. So this is essentially kinetic energy of particles, electrons, sometimes the nucleus. You have the interactions, and the interactions in condensed matter physics, it's the Coulomb interaction, and they may carry some spin and therefore some magnetic moment. So you may have a magnetic interaction or a spin-spin interaction. So these laws are very well known, so this is not at all the problem. Okay, so we know what to solve. The problem is, as you know, is the exponential scaling of the Hilbert space. If you have a system, a single particle which carries d degrees of freedom, when you have n of them, of course, it scales like exponentially d to the n. As of today, the record of ab initio calculation, which is, you exactly solve on a computer the Schrödinger equation for spin 1/2, so the simplest system. So it has been actually held by Andreas Löschli. So when you have a totally random coupling, so you can make nearly no approximation, you cannot simulate more than 50 particles. So of course, we are very, very far even to be able to ask profound questions about phase transition. The system is kind of too small. So, of course, we learn many-body physics, we learn condensed matter physics, we learn high-energy physics, so we know things. And we know things because very often we can apply approximate methods. These approximate methods are not necessarily very well controlled, and sometimes they're even not valid at all. And in particular, when the interactions become the dominant energy scale. I mean, if you think about band structure, essentially it's just the kinetic energy with a little bit of interactions that you add on that. But if you are in the domain of strongly correlated system, the interaction dominates, creates very strong correlation, and it's nearly impossible to apply the usual approximations. And that's too bad, because on top of all the systems that I've been discussing, there are many materials of interest for applications in daily life that can be relevant, and that actually falls into this category of strongly correlated matters. I mean, once again, it's kind of interesting to Google application of strongly correlated materials, and you will find many applications that are associated to harvesting energy, for example, using a solar panel, understanding catalysis process in batteries, understanding what happens at the electrodes of batteries. So these are all applications of strongly correlated materials, where essentially having a good understanding may give intuition of how to build better materials, so better solar cell panel and so on. So we are not there yet, but this is certainly one appealing directions in terms of material science. So we don't know how to do approximations, so what can we do? I mean, there are many ways to do that, but one approach that was suggested by Feynman, you probably all know that, is to use a quantum simulator, which is to say a machine which has been engineered in order to implement the Hamiltonian you are interested in. The thing which is kind of interesting is that this machine may actually implement an Hamiltonian which is totally artificial. It may not be an idealization of a real-life situation. I mean, if you assume that you have a theory friend, comes to you and say, well, I would like to understand the role of such symmetries. I mean, these symmetries may not be a symmetry that you encounter in nature. It doesn't matter. You may be able to engineer these symmetries in your system, and that would help your friend to develop some kind of intuition. So this is kind of an interest. This is what I said by saying it can be mathematical Hamiltonian. One also nice virtue of this system is that, at least on the paper, we can program them in the sense that we can tune the parameters of the Hamiltonian. So one thing that we can in particular do is to tune the interactions between the particle, which is something which is kind of difficult to do. I mean, when you have the Coulomb interaction, you can kind of modify it slightly, but not that much. And you can, for example, separate the influence of impurities from the role of interactions and so on. And also something which is very important is that because the platforms are different from, the real life material that people study by, for example, neutron scattering, you have new probes, and each time you got a different way of looking at the system. Usually it gives you new ideas or new insight into the system. So this also has this virtue at providing you with new ways to looking at a given problem. So, of course, we need systems to do that, and there is, many of them. So I just flash 4 of them here that are actually pretty popular those days. There is the one where we can manipulate ions in electromagnetic traps. I mean, needless to say, it essentially started like a few miles from here, with a group of David Wineland, but so essentially controlling the interaction between ions in order to do quantum computing tasks or quantum information. So you can, with laser, control the interaction in chains or even now in 2D crystals. Atoms that you can place in optical lattices, so essentially these are 2 laser beams or more that you interfere, so you've got nodes and antinodes, and at the position of the antinodes, say, you can put one and only one atom, and you can even measure them and observe them. So this is an example of a fluorescence image taken in Munich of fluorescence image of single atoms that are in such optical lattices. There's the system that I'm going to describe, which is a bit complementary to this one, which has kind of complementary features, I would say. Atoms in arrays of optical traps. And there is also another platform, of course, which is very popular. These are the superconducting circuits, and they are especially popular because they are big companies, so big names developing them. So what is interesting about those platforms are essentially those 3 features. The first one is that now we can manipulate, and that's true for all the platforms that I showed you here, more than 50 particles. So why 50 is interesting? Because as I mentioned, this is essentially where now, if you want to do an ab initio calculation, the theory fails. You cannot do the numerics. And there is a potential, and we're actually near there for many of these platforms now, beyond 1,000, so way beyond what can be simulated on the computer. Second thing is that they have a high degree of addressability. So what is important is that we can apply local manipulation in the system. So for example, change the state of this atom and not the one and this one, or to measure some kind of cross correlation. So it's both you can manipulate, but you can also measure in a position resolved way. So this is very important if you want to build observables that are relevant to many body physics, like correlations, for example. And as I said, they are to a certain extent programmable, and you cannot, of course, do everything you want, but there is this programmability is improving. So the platform I'm going to describe is this one. So that's the one that we have developed at the Institut d'Optics together with a few other groups. And so essentially what I will try to do from now on is first to try to introduce you to the platform, which we will call this Rydberg quantum simulator, which combines 2 features: arrays of individual atoms in optical tweezers that we make interact by promoting them to Rydberg state. And I will show you 2 examples of simulation which we've done, which are relevant to quantum magnetism. One is to implement the Ising interaction and to study the quantum Ising model in a way that we'll explain. And the second is we'll use another kind of naturally occurring interactions between Rydberg atoms to study what is called XY magnets. So it's just, I'm not sure that you're going to learn many things in many body physics. It's just to illustrate the kind of tools and that we have in the labs. So let me start with describing the platform. So essentially it started actually at the Institut d'Optics nearly a quarter of a century ago now. So Philippe Grangier, we managed to trap a single atom for the first time in an optical tweezer. So an optical tweezer, this is nothing but a laser, so exactly like the one I have in my hand, a few milliwatts of laser light that you focus very tightly using a large numerical aperture lens. There are various ways to do that, it's not too important, but essentially you have a spot. This spot is focused on a size of about 1 micrometer, so the wavelength of the light you are using. And it turns out that if your laser is not exactly resonant with an atomic transition, you can create a potential here, which is totally conservative. So essentially, you can create like a ball here where an atom is going to get trapped. It's just that the depth of the ball is very small. It's typically a millikelvin. So you need to start from cold atoms. So that's what we do. We start with all the machinery that people have developed, in particular here, but also in Philippe's group, in many groups around the world in the between 1980, essentially, and 1990. And so we create this reservoir of cold atoms using what is called magneto-optical trap. It's not too important, but using laser beams that kind of cool the atoms down. And this kind of ensemble of about 1 million atoms at 100 microkelvin is going to act as a reservoir for the dipole trap. Okay, so the atoms are going to enter and leave at random place. So the reservoir contains atoms at about 100 microK. So we use very popular atoms, which are rubidium atoms. And the thing which is nice with this setting here is that you have two lasers. There is a laser to trap, which does not induce any fluorescence. It's very far from any atomic transition. And you have the laser that ensures the cooling and that at the same time provides you for free with photons that you can image on the camera. So essentially, you collect the fluorescence induced by this laser cooling. So now if we look at the pixel of the camera that we're using, and which is essentially supposed to image the place where the atoms is trapped, we observe this kind of telegraphic signal, so essentially a low level, which corresponds to the background noise in the experiment, and then suddenly there is a jump, and this jump is precisely the signature that there is an atom that enters. And the thing which is striking is that in this setting, you never have a double jump. So essentially, you never have two atoms at the same time. So why is it so? So the thing is a bit subtle, and I'm not even sure we fully understand that. Actually, for example, Cindy Regal here is looking very closely at the nature of the mechanism, but yet it works. When you have a step up here, essentially it means that an atom has entered in the dipole trap, and it's kind of cooled by the laser cooling, by the cooling laser around. So essentially you damp the motion. And when a second atom enters, what happens is that the cooling light will create a molecule. And this molecule is a highly excited molecule which will decay extremely rapidly. And first, the two atoms found themselves very rapidly because there is a very small volume. And you expel the two atoms. So essentially, what you have is just zero atom. One atom enters. And here, if we add the resolution, we will see a double peak where a second atom enters, and you lose the two of them extremely rapidly. And so this is this mechanism that, in a sense, ensures that you've got a non-deterministic single atom source. In the sense that you can now put a threshold, so you decide there is no zero atom if you are below the threshold, and when you are above the threshold, you know that there is one atom, and you can start the experiment. Of course, the non-deterministic aspect is an issue, because you don't know when the atom is going to enter, and therefore you don't know when to start. It means that you need to wait until the atom sends you a signal to start your experiment. So now, of course, you want to have many of these atoms. So just here, before I do that, I just present you kind of the zoo of atoms that have been a single atom trapped those days. So we start to have a fair amount of them. And so I hope I haven't forgotten any. Essentially, all the atoms in green and red correspond to the atom that have been laser cooled so far, neutral atoms. I'm not talking about ions. And the ones that are in red are the ones that have been single atom trap, essentially along the idea that I've just discussed. So you've got, for a very long time, the alkalis were very popular, and now we are like joining the crowd with many more atoms. Okay, so in particular, here at Gila, Adam Kaufman started with ytterbium. There is also strontium. Okay. So now we want to have many of them because we want to have to do many body physics. So how can we generate many of these traps? In a very simple way, just by diffracting the light that we use, the laser beam that we use to create the trap. So essentially, we put a diffraction grating, which actually turns out here to be a phase mask, that imprint a phase, and what we have in the Fourier plane, or in the focal plane of the lens, is essentially the Fourier transform of the mask that you have imprinted on the spatial light modulator. So for example, with this kind of mask here, you would have an array of laser traps. The problem, as I said, is that it's a non-deterministic atom source. So essentially, if now I take a real-time image on the CCD camera of the array, so this is a 27 by 27 arrays of beams, and you see the atoms blinking in the sense that there is an atom that enters, and when it switches off, it leaves the trap. But you see immediately that the big problem is that we never have all the traps filled at the same time. So it's kind of a problem, because if you want to arrange them in a given geometry, you cannot do that here. The idea was actually reasonably simple. That was a big problem for a long time for the platform. And the idea was actually demonstrated initially by the group of Dieter Meschede, and then there was initial work in our group. But the full-fledged version of it was designed in 2016. The idea is actually kind of simple. You just take a first image, and you look at where the atoms are. Okay? And then you switch off all light, apart from the trapping light, and you just add an extra laser beam, and this extra laser beam is going to take an atom from a filled trap and bring it to a trap which is empty and that you want to fill. Okay, so in this way, you assemble atom by atom the geometry that you wish, and you can, for example, starting from there, have this kind of 200 snaky atoms that are now have no holes. So each of these fluorescence images are single atom, single shot fluorescence image. Okay, so now we do that routinely, and there are many, many labs who do that around the world, but still we need to remember that what we're carrying is just one and only one atom, and we carry it over micrometers and over like fractions of milliseconds. So the process is kind of very efficient, and so those days where we can assemble nearly 300 atoms in various geometries, so typically this 1D stuff, 2D, which is going to be useful in the talk. We can even have totally random structures. So you may have recognized here a very ugly pixelized version of the Mona Lisa. So it's totally we did that during COVID when the museums were closed in Paris. And then we can even assemble them in 3 dimensions, although we haven't done any physics with this, and neither with the Mona Lisa. Okay, so very nice. So now we've got these arrays of atoms separated by many micrometers. Distance can be a few to tens of micrometers. So the big issue now is that, of course, the atoms are pinned in their trap. They cannot jump from one trap to another. There is just no tunneling. So you need to find a way to make them interact. And this idea and the way to make them interact was actually introduced in a slightly different context at the time by many authors. I mean, we always remember Michel Lupin and Peter Zoller, but there were other people on the paper as well. And it was taken seriously by Mark Safman and then a few months later by us. But the idea is to excite the atoms to Rydberg state, so highly excited state of any atoms. So any atoms can be made a Rydberg atom. So that corresponds to very large principal quantum numbers. So the kind of classical version of this is this kind of solar model where you've got the electrons cycling very far, spiraling very far from the nucleus. Typically, it can be, the size of the orbit can be 100 nanometers to 1 micrometer. So this is a very sizable object at the atomic scale. The important features of this are twofold. The first one is that if you are in a Rydberg state, because you've got such a large orbit in a sense, and you hardly radiate any energy, so the lifetime is going to be much longer than if you are in a low-lying state. So typically on low-lying state, you would have tenths of nanoseconds. If you are in the Rydberg state, you can enhance by 4 orders of magnitude the lifetime, reaching several microseconds or even milliseconds. So that doesn't look like a lot, but as you will see, it's enough to do many body physics because we are making use of the second important properties, which is kind of intuitive here. The plus and minus charges are very far from each other, therefore there is a huge dipole. And the consequence is that you can induce large dipole-dipole interactions. So the kind of typical figures that we have are for atoms separated by about 10 micrometers, which is a really large atomic scale. The strength of the interaction for the typical Rydberg state we use is in the megahertz range. So it means that any dynamics induced by the interactions is going to be sub-microsecond. And you see that sub-microsecond means that the lifetime is actually 100 times longer. So indeed, you can hope studying many body physics in a coherent way, to a certain extent, ignoring the lifetime of the Rydberg. Okay, so this idea of controlling that, as I mentioned, was put together in the early 2000s. It took kind of nearly a decade to actually show that in the lab by bringing together this individual atom manipulation that we had, for example, in Institut Optique, but also in the group of Mark Safman, and to have the control to do that. So we did the first experiment around 2009 about that. And I should say that, as James mentioned, now it's an extremely popular platform. There are really many people doing that. I mean, there was some very inspiring work being done here. There are many variants on how to prepare the array, so I'm not going to detail that too much. But essentially, the field is moving in many different directions. And an interesting one, for example, is to trap molecules, or even to do the engineering of individual molecules. Just one atom of a given species, another atom from another species, merge them in the same tweezer, and then photo-associate them. So this is what Kenkenui does, for example. You can even trap directly molecules like CAF. People are actually now extending the capabilities with dual species array. So this is in the group of Hannes Bernian in Chicago. Here in GILA, so Adam Kaufman has kind of pioneered the combination of the optical tweezers with optical lattices. So you now can use the tweezer to place the atoms where you want in a lattice. There were this actually kind of spectacular work from a few weeks ago, and also from Atom Computing and close by, where now people are able to assemble arrays of 1,000 atoms without any defect nearly. So this is kind of spectacular. This shows that we can really scale up at least to a few thousand the number of atoms that we control here. So as I said, and James mentioned, I mean, now the platform is popular, it's scarily popular, I would say. For us, the competition is a bit fierce. So there are more than 200 of these experiments in construction worldwide, and I'm not even including China because I don't know how many there are there. But the motivations are actually moving in many different directions. Optical clocks and metrology, and that's certainly a direction pursued here at GILA. Quantum simulation in many groups, quantum computing, but also to use them as a new kind of light-matter interface. So what I'm going to focus on now is more the quantum simulation aspect, and we're trying to walk you through how you go from these arrays of individual atoms which you can make interact to actually something that people are interested in condensed matter physics. So it turns out that actually the Rydberg atoms have two ways to interact. And I will detail the two of them. But you can either interact with the van der Waals interaction. So this is the natural interaction that occurs when you place two Rydberg atoms in the same Rydberg state. Okay, they will have kind of a diagonal shift, which is the usual C6 over R6 interaction energy. You can also have another configuration, which is called the resonant condition, where essentially you've got an atom in a Rydberg state, let's say S, another one P, and the angular momentum, or vice versa. This is degenerate, and in this case, you've got a resonant interaction, which scales like 1 over R cubed. So I will say more in a minute. But the nice thing about that is that you can view this ensemble of atoms interacting by either van der Waals or resonant dipole as implementing spin 1/2 models, in a way that will become clear in a minute. But essentially, you just assume that you've got arrays. The atoms are pinned in space, or the spin are spins in space. And the van der Waals will implement what is called the Ising model. This Ising model, I mean, is the first model we usually encounter in StatMech and when we learn physics. This is the easiest one to describe, and it's relevant to magnetism, for example. The second model is called the XY model. This is a flip-flop interaction. And once again, I will say a bit more in a minute. Sigma I plus sigma J minus, so those are the Pauli operators. And this is relevant, for example, to study magnetism first, but also transport of excitation. I mean, you can imagine that you have kind of a bunch of spin down. You place one of the spin up, and you look at how it propagates due to this flip-flop interaction. So this is one way to study transport. And for example, you want to model what is called the conductivity of organic polymers. I mean, this is a model which is fruitful to describe that. It's also a model which people use to explain or to describe chloroplast, you know, this light harvesting device in biology. So, okay, so let's try to start with the Ising magnet using the van der Waals interactions. And what I will try to walk you through is how, starting from something which has nothing to do with spins, we can recover the same equations as the one of what is called the transverse field Ising model for spin 1/2. So once again, we have the van der Waals interaction. So the van der Waals interaction is the interaction that occurs when you take two Rydberg states and place them in two atoms, and place them in the same Rydberg state. The interaction is C6 over R6, but the thing that makes Rydberg so special is the very violent power law for the C6 coefficient. So it scales like the 11th power of the principal quantum number. So this is pretty dramatic. Apart from the exponential, there are not so many laws in physics that vary so violently. And it means that the interaction is switchable. Why is that so? Remember, you've got the atoms a few micrometers away. So in their ground state, if we just take rubidium, n equals 5, essentially there is no interaction. It's totally negligible. Now you go to n equals 50, which is very standard in this field. You enhance the strength of the interactions by 100 billion. So this is actually quite a strong thing. So it means that now the atoms can interact very strongly. If I want to describe that by an Hamiltonian, I'm going to write a diagonal Hamiltonian, which is of the form C6 over R6 times N1 and N2, which are the operators that counts whether an atom is in the ground state or in the Rydberg state. So essentially, unless the two atoms are in the Rydberg state, in which case N is equal to 1 for both of them, otherwise, this Hamiltonian gives you 0. Essentially, there is just no shift. So this is just the translation of the fact that two atoms only interact if the two of them are in the Rydberg state. Okay, so now, of course, now you need to excite them to the Rydberg state, and naturally in the tweezer they are in the electronic ground state. We do that, there are different ways to do that, but essentially in our case we do that by a two-photon transition. So I'm going to completely ignore the details that actually annoys the PhD students in the lab quite a lot. So I'm not giving credit to their hard work, but essentially this now we're going to say it's a spin 1/2. Spin down is the ground state, spin up is the excited state. It's coupled here by the lasers. the only practical thing that you need to do to know is that the Rabi frequency coupling the two states is the square root of the laser power. So it's a bit depressing and costly because we need a lot of laser power to do this. And the laser beams kind of illuminate the entire array. So now if I write the Hamiltonian that describes this ensemble of atoms that can interact when they are in the Rydberg state and which at the same time are driven by the laser, I will have actually three contributions. The first contribution is the C6 over R6 and INJ, which looks like an Ising interaction. And the second is this part here, which is essentially the Pauli matrices saying that you can go from spin down to spin up. And it turns out that on top of that, if your laser is not exactly detuned, there is an extra term here, which is a sigma z, sigma z. So now, these equations are exactly the same as the one you find in textbook in quantum in statistical mechanics. If you take an ensemble of spin 1/2 interacting by an Ising interaction and place in a magnetic field with a longitudinal and a transverse component. So this is the idea of all that, is that essentially you emulate your transverse field Ising model by an ensemble of atoms interacting by the Rydberg interaction, the van der Waals interaction, and driven by the laser. But of course, in our real system, there is no spin, there is no magnetic field. It's just emulated by lasers on Rydberg interactions. And the thing interesting is that we can control the parameters for essentially making the interaction totally negligible to making it the dominant energy scale. Yep. Good. So let's try to illustrate that on a very simple example. We start by an array of 10 by 10 atoms. So each of the dots corresponds to one atom in the ground state, in their electronic ground state. And so what we're going to do now, we're going to choose the coefficient in the Hamiltonian, we just to choose the parameters in such a way that the nearest neighbor interaction is on the order of the strength of the magnetic field, the transverse one, so the omega, the Rabi frequency. So what this means is that now if I have an atom which is excited to a Rydberg state at a given location, it will cost too much energy to excite an atom at the nearest location. So there is some kind of blockade of the excitation. So now, if I just add another excitation and I place it here, this is at 0 energy cost, okay? Because essentially the atoms are too far to interact. I can place a third one and so on and so forth. And so now if you ask yourself, let's add even more interaction, what is the tightest packing I can get? It's essentially exciting every other atom. And actually, if we do the experiment, so we vary the parameters of the lasers in order to add one by one the excitation in the system, and we take an image at the end, we've got this kind of fluorescence image. So this is kind of something which looks a bit like this, apart from the fact that every other atoms are missing. So why are they missing? Actually, they are not missing. It's just that they have been excited to the Rydberg state. So here you have to believe me. It turns out that the detection scheme that we use make a Rydberg state dark. Okay, so essentially this configuration that you have of dark, bright, is the exact implementation of an antiferromagnet, or so to say, a Néel order that you have, an antiferromagnetic order. And this is the kind of magnetic order that actually people find in real materials. And you've got some iron oxide, for example, cobalt oxide, that are actually an antiferromagnetic order. So I should say that actually those were experiments done in 2021, and there were many groups that actually have done kind of equivalent experiments. So this is very neat, but what do you learn? You don't learn much from the point of view of the physics, and this is essentially trying to pack balls close to each other, the balls having a size which is essentially this size. So this is not that you've learned a hell lot of things, apart from the fact that you know how to do it in the lab, which already is not so bad that you're able to do it. But it turns out that when I add the excitation here, it's a dynamical process. And I was mentioning at the very beginning that it's very difficult to simulate dynamics in a system when you place it out of equilibrium, which is essentially what we do here. So I'm not going to tell you so much about that, but essentially the only point I would like to make is that when we try to simulate the dynamics when we were adding the excitations, we had to cope with a many-body system. This many-body system was at the same time driven, and so we asked Andreas Löschli to run some simulation to follow, for example, the magnetization that you would have here. And every single curve that is simulated for us, including the noise, took 14 days for 10 by 10 array on a supercomputer. So it just tells you that it is already challenging the computational power, and this was using state-of-the-art what is called matrix product state method in 2020. Now people have improved, and the improvement is actually in part due to the fact that people in the lab have now manipulating larger number of atoms. So this is one virtue of these platforms, is to tease a bit the theorists and encourage them to improve their numerical method. So, I mean, we don't necessarily learn a lot from the point of view of the physics, but now you can benchmark numerical methods against experiments. The second thing still is that you can also explore some kind of new phases of matter. So the kind of thing, I'm not going to say much, but that we have explored as well, is the quantumizing model in the framework of, in the case of triangular arrays, because then you've got what is called a spin frustration in case of antiferromagnetic coupling. I mean, you're probably all aware of this work that was done in Harvard, where people have trying in the group of Misha looking to prepare spin liquid. And so those were long thought phases of matter. They're very difficult to detect actually through regular, condensed matter with regular condensed matter probe. And here they are the way to emulate this and to find a state which looks like a spin liquid. Right. So this is what we can do with this kind of arrays of tweezer. Using the van der Waals interaction. So I would like to show you another type of application just to enlarge a bit the class of Hamiltonian we can look at. So I looked at the transversizing model and transverse fieldizing model, so ZZ type of interactions, and also a term which is an X, and the two parts of the Hamiltonians do not commute, and so that's the reason why it's called the quantumizing model. Now we're going to look at another type of model which results from the resonant dipole interaction. All right, so we've explored this, so now let's explore the second kind of interaction. So now everything we're going to do will be in the Rydberg manifold. So previously for the van der Waals, we had the true electronic ground state of the atom, that was the spin down, and a given Rydberg state, that was the spin up. Now we're going to totally forget about the low-lying state. The spin down will be state S, one Rydberg state, and the spin up will be a nearby Rydberg state, coupled by a transition that's typically 17 gigahertz. And this transition you can drive with a microwave. So remember that, it's an important tool that I will use in what is going to come. So you just shine your microwave and you can drive Rabi oscillations between those two states on a single Rydberg atom. Okay, so once again, everything now is a Rydberg atom. The spin down will be the lowest Rydberg state, and spin up will be the highest Rydberg state in those manifolds. But so from the point of view of the interaction, now you may have these kind of situations where one atom is in spin up, the other one in spin down, and due to the dipole-dipole interaction, they actually exchange their states. So essentially, this guy goes down, emitting virtually a photon in the electromagnetic field around the atoms, which is caught by the second atom nearby. And so this leads to the d² R³ interaction, which you can observe in the lab. And so this is an example of two atoms located at 15 microns, separated by 15 microns, sorry. You place one in spin up, the other one in spin down, and after some time you kind of measure the state of each of the atom, and you do observe that these states oscillate in phase opposition, as they should, because they are exchanging their state. You also see that it's damped because it's an experiment and not theory, so there are some limitations that we are trying to understand and to overcome. But so essentially these implement this sigma plus, sigma minus type of interaction, which people in condensed matter physics prefer to write as an XX plus YY interactions. And that's kind of useful to remember that. I will explain you in a minute. Okay, so what is the question we're going to look at now? We're going to look at what is the ground state properties of an ensemble of small magnets, so spin 1/2, interacting 1DXY model. But the thing that is going to be interesting here is the fact that the interaction range is a 1/R³ interaction. It's not just a nearest neighbor interaction, as the 1/R6 is essentially, and because it's decaying so quickly that you can kind of ignore the tail to a certain extent. But here it's really longer range interactions. So this is relevant to Rydberg, obviously, but not only to Rydberg, to most of the platforms that I have described in one of the slides where I'm showing the platforms, and the dipolar molecule, as explored here in June's group, for example, but not only. For magnetic atoms, you can take atoms like chromium, erbium, dysprosium. They have permanent magnetic moments, so they're also kind of going this kind of interaction. You can even use defects in solid, and the nucleus of the magnetic moment of a carbon-13, for example, may interact with the one of a vacancy, the Rydberg atoms, obviously. So why is the 1/R³ interesting? Is because from free, so to speak, you will have frustration. And frustration is something which is very hard to simulate in condensed matter physics when you have a frustrated situation. So what is it about? If you now assume that you've got an antiferromagnetic ordering and you place your atoms on a square here, the antiferromagnetic ordering is going to favor that this spin is up while the other one is down. This spin is down, the other one has to be up, and so on. But the consequence is that you've got a ferromagnetic ordering along the diagonal. And this is in opposition or in competition with actually the naturally occurring antiferromagnetic ordering here, which for sure is weaker, but still exists and will have a tendency to destabilize this ordering here. Okay? So the question we're going to ask is, what is the ground state of this ensemble of dipolar magnets? So the reason why I wrote this kind of Hamiltonian in the XX plus YY is because it tells you already that things are more quantum, so to speak, than the Ising model. The Ising model is a classical model, and essentially when we learn that in StatMech, it's essentially saying that you can have either Ni equals 0, Ni equals 1, so it's how tightly packed you can put your balls on the array. Here you've got two competing orders. I mean, the two parts of the interaction energy, actual Hamiltonian, do not commute. So this part will have a tendency to impose a given order in the direction x, while this one will have a tendency to put it along the direction y. So in a sense, you've got some kind of superposition of having the spins pointing in different directions. As a matter of fact, we don't know how to write the state of the ground state, the ground state of the XY Hamiltonian. There is no analytical formula, but you can write some kind of wave function on that. So this is an example of them, where essentially for the ferromagnetic case, you're going to say, I take a classical ferromagnet, ferromagnetic state, so all the spin pointing in one direction, and I'm going to make a superposition of all the possible orientations of this. So this is actually a good ansatz to describe a ferromagnet ground state of this Hamiltonian. And for the antiferromagnet, it's the same, but instead of rotating the ferromagnet, you rotate a classical antiferromagnetic state. So it's a kind of a superposition of mean field, if you wish, state. As I said, the dipolar interaction leads to frustration. And there were some kind of predictions that are actually not so old, but about what should be the ground state in the presence of now long-range order. It turns out that if you work at T equals 0, so 0 temperature, then you should have, both for the ferro and antiferromagnetic case, you should have a long-range order. So what people call long-range order, if I understand correctly in condensed matter physics, is the fact that you look at the correlations, the spin correlations, let's say along x. So the correlation tells you if I have a spin along x here, what's the probability to have another one with the same alignment, a distance I minus j away. And it turns out that if you have long-range order, essentially the spin correlation never goes down to 0. You have an order even when the spins are infinitely aligned. So this is what people call long-range order. And in part, so at T equals 0, you are supposed, both for ferro and antiferro, even in the case of one over R cube interaction, to have this long-range order. But now, if the temperature is not equal to 0, things will be different, because it turns out that the ferromagnetic order is robust with respect to the temperature, the thermal excitation, if you wish. While, due to the frustration, which kind of destabilizes the order, you would not be able, at T non equal to 0, to sustain and to maintain this long-range order. And it turns out that this long-range order in 2D XY magnet has never been observed experimentally on any platform. So what I will try to show you is one observation of this. So this is something we've done once again with Norm Yao, and I just try to show you how we do that experimentally and how we can access the ferro and antiferro. So we start from our resource Hamiltonian, which is an XX plus YY Hamiltonian. The coupling is ferromagnetic, okay? And you cannot change the sign. It's ferromagnetic. What we're going to do, we're going to add here the equivalent of a staggered magnetic field. And we're going to play with it. So in the following way, we start by preparing what is called a classical Néel state. So essentially, we start by applying a magnetic field, which is kind of staggered, and which will create, in the z-axis, an antiferromagnet. So how do we do that? So we start with all our spin that are down. So this is the initial state that we start from. And we're going to apply laser beams. Those laser beams are precisely this term. But we apply the laser beams every other atoms, and what the laser beams do is that they shift the resonance of the atom. They apply a light shift. So now, if I apply a microwave, I will be able to flip the atoms who do not see the light shift because the microwave is resonant. And essentially, I can create this kind of staggered configuration of spin up and spin down. Okay, just emulating, and this is again in the presence of this strong magnetic field coupled with the microwave. So now I have prepared a state with zero magnetization along Z. And remember, what we want at the end is a magnet in the XY plane. So it also needs to have zero magnetization along Z. And so the thing which is neat now is that just by choosing the sign here of the detuning, if you wish, or so to say the sign of the magnetic field, we can either access the ferro or the antiferromagnetic state. Why is that so? Assume that I were starting from, so this, sorry, I should first say what is this. So this is kind of the exact diagonalization of the interaction energy of this Hamiltonian. So essentially, you've got the interaction as a function of the control parameter, which is this delta here. What you find is that there are many lines, and it's done for 2 by 3, so 6 atoms. But let's assume now that I start from this state with delta negative. So I'm here. Okay? And I will sweep adiabatically this, and what I can do is to connect to this state when there is no detuning any longer. So essentially I started in the Z plane and I melt gradually this into the XY plane. I connect to the most highly excited state, which is, because J is positive here, the antiferromagnet. The thing is that if I just change the sign of the magnetic field, or so to say the detuning of our laser, and I do the same thing, now I can connect to the ferromagnet. So you see that with a given sign of the interactions, playing this trick, we can excite either the lowest excited state or the most highly excited state. It's a zero temperature problem, so it doesn't matter which one I look at. And I can do then a comparison between the behavior of the antiferromagnet or the ferromagnet. So let's do that in the lab. So once again, I have this thing where I can vary the light shift. I start having prepared my antiferromagnet along Z, and I run down. After some time, we're going to read out the magnetization and the correlation, so the state of each of the atoms in the X plane. And so we're going to build this kind of correlation map. So essentially, this is a sigma X correlation, which once again signs the probability that if you have a spin up at a given direction, you get a spin up in another direction, so along X. So it has to be a square thing, so because it's 2D. And I have either something which is all red, which signs the fact that they all have the same order, the ferromagnetic order, or I can have this thing where I have a staggered blue, red, which actually is the signature of an antiferromagnetic correlation. Blue meaning negative correlation, red meaning positive correlation. So it's a staggered configuration. We can plot that now as a 1D graph just by averaging over all the atoms located at a given distance d. So that makes this 2D graph a 1D graph. So now I have the correlation as a function of the distance. Yes, as a function of the distance. And we have two very different behavior depending whether we had started from the ferromagnet or from the antiferromagnet. If we were starting from the ferromagnet, we see that indeed the correlations never decay back down to 0, and which is exactly this long-range order that we were looking for. On the contrary, the antiferromagnet, the correlations are shorter range, and on top of that, they decay down to 0. So essentially, what this means is that we have observed a long-range order in the case of the ferromagnet, while for the antiferromagnet, the little imperfections of the experiment combined with the frustration kind of destabilize the order, and we are not able to observe a long-range order. Sure. Because we check that. So in the experiment, we vary the time scale and make sure that what we observe at the end doesn't depend any longer on the exact time scale that we choose. Yeah, and so the second thing then is that people have done, the theorists have done the calculation for smaller systems, I have to say, because for such a large system, they cannot do it. And they tell us that the ramp is supposed to be adiabatic. I mean, of course, I can never definitely prove that. I mean, I would need an infinite coherence time to be infinitely slow. But you are raising an important point, which is all this adiabatic preparation, obviously, on those machines and on any of those machines, whether it's this or optical lattices or superconducting circuit, it's very difficult when you grow the size of the system to stay adiabatic because the gaps kind of scale down. It turns out that here the gap scales down not so widely. It's 1 over the root of the number of atoms. Okay. Yeah. Sorry. Yeah. So that's a very good, it's a kind of a constant fight between us and the theorist. Strictly speaking, we don't have a temperature. The system is, when we initialize the system, we have some kind of holes, for example, or some kind of defects. Not all the atoms have been prepared. So essentially what we should say instead is that it's a non-zero entropy state. Okay? So this is rather the imperfections in the state preparation that kind of be, entropy divided by Kb, whatever, has to be the temperature. Okay, so this is just this way we define the temperature. But it turns out that the theorists we interact with always want to call it a temperature. For me, it's more the fact that we have entropy that we've injected in the system. And the entropy is not negligible in this. We pay, yeah, it's significant, the entropy per particle. But you wanted to add...
Yes. So if you think that if you do a fine size scale, you can
Yes, but we have never tried to do that. But yes, we could try to do this. Yes, we try to see the square root. Okay, so that's essentially, it shows that this 1/r cube does play a role there because you've got this differential measurement between ferro and antiferro, and in principle, it should be due to the 1/r cube interactions. But I mean, it's more just to show you the kind of tool we can, trick we can play. So things that we've done, and essentially I'm done in 5 minutes, if it's fine, is you can also still enlarge the class of Hamiltonian that you build. So we have the van der Waals, which emulates Ising. We have the XY 1/r cube. You can combine that with microwave, do what is called Floquet engineering, and engineer a full XYZ type of Hamiltonian. This is one example. Another thing, we can also play with the atomic structure, and we can induce what is called a spin-orbit coupling. So this is an example of placing an excitation up at a location, and this excitation, instead of propagating symmetrically, actually, if we play with this kind of trick and the magnetic field, we can make the excitation that actually rotates in a given direction depending on the sign of the magnetic field. So this is kind of a tool which is also interesting to explore topological features in those systems. So hopefully it kind of shows that these machines operate with a large enough number of atoms that it's actually hard to simulate exactly. And the antiferromagnet, for example, I just showed you in the XY model, the theorists could not do even a Monte Carlo simulation of that. It's just too hard. It's a sign problem for this number of atoms. So they had to do that for smaller system size. What I would like to finish off with is trying to show you that those machines, which I looked at essentially through the eyes of quantum simulation, they can do more things actually. And one thing that they can do is they can also look at applications. And so one application that people are considering are optimization problems. So you just take, for example, here, this is the electricity grid in the US, and you've got places where you produce electricity, other places where the things is routed, so you've got some kind of hub. And of course, what you want is that this grid, and that's true in every country, it's not only in the US, it's stabilized at any given time. And this is actually very difficult to do, because it means that if suddenly the windmill produces a little bit more, you may have a problem that you have too much electricity produced at one point, and essentially the grid kind of gets destabilized. So when you want to model that, so people doing a logistic problem, and this is a logistic problem, how you flow the current to this grid, the same thing as when you've got the guy, the delivery guy, you know, from Amazon, kind of dropping parcels. He has to kind of minimize the length of his road, essentially, his trip. They write some kind of cost function. So a cost function is essentially, has two terms, usually. The first is that you need to couple one point to another one. So this is an Ni and J. So if you have 1 and 1, it means that you connect the side I and side J with some kind of coupling, which I'm going to comment on. And you usually add also an energy penalty, just to say, for example, here I don't want the current to go too much through this node, because otherwise I will burn and blow the grid. But you see that immediately this is just nothing but the Ising Hamiltonian. So essentially, if I found the ground state of the Ising Hamiltonian, in a sense, I have solved the optimization problem. So that kind of looks easy on the paper, and there are a few problems. The first one is that the Jij may not be the one that you can implement on your platform. For example, I may want that this guy and this guy are connected, and this guy are also connected, but with the same strength. With interactions, I cannot do that. An interaction has a given power law, so I mean, you need to find ways to embed this kind of graph in a larger graph. So of course, there is an overhead to do that. It turns out that when we look at, and that was work that was done in collaboration with EDF, we look at the kind of algorithm that EDF, so this is Électricité de France, so the French electricity company, what they could do essentially, they say, well, you can, if you know how to manipulate now more than a few thousand atoms, you should, for certain type of algorithm, of problem, sorry, do better. You can be competitive with this quantum approach with respect to the heuristic algorithm that they are using. So usually they have heuristic algorithm that do not necessarily know whether this is the best solution, and that could be tested with those things. So, I mean, the good news is that it's only 2,000 or 5,000 or even 10,000. The good news is that it's not 1 billion, because then, I mean, there is no way we're going to do that in the near future. So we'll see whether indeed we can reach this point. Second thing which is interesting, and here, I mean, I know who I'm talking in front of, quantum metrology. So this idea is that you can harness the correlations between the particles, for example, using squeeze state, and use those correlations to enhance the precision of a clock. And what those machines do precisely with the spin models, so these interacting atoms, is that they spit a state which can have this kind of correlations. Okay, so this is a way to engineer this kind of more precise clock. And I mean, just with arrays of atoms, there were actually a few papers around as of last year where we had showed that together with Antoine Kaufman, for example, Monica Schleyer-Smith and ourselves, that using Rydberg platform, you could indeed produce those states that were showing this squeezing and these enhanced performances in terms of metrology. And of course, there is a kind of a long, still very long, despite the many progress towards the road towards quantum computer. And just using the Rydberg platforms, actually, there are some kind of very impressive work on the group of Mark Safman in particular, but also Misha Lukin. So this is just looking at baby algorithm, but this is going in this direction. And just to finish off, essentially, I mean, you mentioned the fact that we had created this startup company. So it was in 2019. The company is very large now. It's 200 people. So it's really large. So the idea and the motivation initially were actually not necessarily very visionary on my side. Just take the mess in a lab and put it in a shiny box. Well, you hope that it does a bit better than that on top of that, what is in the box works better than what you have in the lab. So it's really trying to engineer as much as we can the technology which is mature enough in the lab. And to dedicate that to engineers, essentially, because for us, the PhD is a bit short. We cannot do this kind of thing in the lab. Second thing, which was kind of appealing, is can we apply or look at applications with this machine. So it's a bit along the lines of what I showed you in the last slide, and the fact that you can already look at real-life problem. So this is exactly what the company has been doing. So I'm not talking about quantum advantage, whatever. Right? Okay, I'm just saying, for the moment, we take a real-life application and we see whether this real-life application can be looked at with the machine. There is no more pretension than that at the moment. Of course, you would like that this thing at some point becomes better than any classical method that you have. But we are not there yet. Just exploring whether we can do that. And indeed, they've done that, in assessing financial risk management. So you go to your bankers, and he has, through an algorithm, to decide whether you will be able to reimburse the loan that he's going to give you. So this kind of thing. There are also some kind of quantum machine learning type of task. And with that, I should mention that, of course, there are some companies, and also just with this platform, there are actually 5 companies now worldwide. So there are 3 in the US, so Quera, Atom Computing, Inflection. So those 2 ones are actually here, actually for some of their branch. And there is one in Germany, Planck as well. So, I mean, there is something funny. When you're in the US, you need to have a black background in the logo, it seems. So, but OK. And so with this, thank you very much for your attention.
Thank you for the beautiful talk. We have time for 1 or 2 questions. Sure, David.
Beautiful talk.
Thank you.
Just wondering, we talk about Van der Waals interactions as pure 1/r physics, but on the length scales that you can control, don't you have retardation effects?
Okay, so
those at all important?
So that's a very good question. So the wavelength, essentially, the 1/r axis branches to a 1/r7 at long distance. But the problem is the long distance is the wavelength of the transition, and those transitions are in the tens of gigahertz. So that corresponds to really distances more on the millimeter or centimeter scale. And therefore, although you're right, we are not far enough to observe that.
Would
But
it have any impact? Probably not.
Ben, your question is a very important question, because I mean, what I mentioned is we emulate a spin model by a physical system which we believe is governed by the same equation. Of course, this is an approximation. I mean, for example, I've neglected also the quadrupolar interaction, and that may play a role, and so there is a big